Hello, everybody, and welcome to the weekly CosmoQuest Astronomy Hour. This week, it's me, Emily Lakdawalla of the Planetary Society, hosting, with Fraser Cain of Universe Today being my beautiful assistant. We're here to talk about what's going on with the Curiosity mission to Mars. I'll give a relatively brief update, I hope, although I have some pretty pictures to show you that I may linger over. And then I'll take and be happy to answer your questions. Fraser will feed them to me. You can put the questions in the comments on pretty much anywhere, on the YouTube video, on my blog, on in Google+, or you can post them to Twitter with the hashtag CQX, #CQX, and Fraser will find them and he will feed them to me. But first of all, let's go on for an update on what's going on with Curiosity. It's actually been a long time since I've done this on Google+. So if I can summarize briefly what's happened in Curiosity's mission after landing, it did some initial checkouts, and then the scientists got a few days to work with the rover in a period that they called intermission, while they drove to a likely spot where they could begin testing the arm instruments. And so that's what they've been doing for the last 6 sols or so, is testing out the robotic arm and what's called the contact science instruments on the robotic arm. That includes 2 instruments. One of them is MAHLI, which is an acronym for the Mars Hand Lens Imager. And the other one is APXS, which is an alpha particle X-ray spectrometer. MAHLI is it's a camera on the end of the arm. Spirit and Opportunity have similar cameras, except at least similar in concept, but MAHLI on Curiosity is so fantastically superior to the microscopic imager on Spirit and Opportunity. There's really no comparison. It's a fabulous high-resolution, full-color camera capable of focus from everywhere from a couple of centimeters to infinity. So Curiosity can actually carry it up and look around with it. It actually took a self-portrait photo, like a Facebook photo.
Have you got that picture queued up?
I don't have the picture queued up, so if you could find it, that would be great.
Oh, sure. Okay, yeah, I'll find it. It was a great picture. You did a lot of work on that, so you should be...
I did. Yeah, it's an absolutely fabulous photo. That's one that I've been waiting for.
Have you got the belly one too queued up?
I do have the belly one queued up.
All right. I'll find that one. That was a good one.
I'll show you that in a second. So this is, this is what's so spectacular about that camera. It's actually the widest angle color camera on the rover, so it'll be quite useful for taking wide angle shots of Mars. It's actually the best one for the sort of dolly cam shots as the rover is driving along. Of course, when it drives, the arm is sitting on the shoulder like this, so it can't drive with the arm out. But whenever it stops, it can pop the arm up, like a little periscope, take a picture, put it back down again, and keep going if they want to. So they took a self-portrait with that. They also took an amazing, what's called the belly panorama. This was the first opportunity that they had to look underneath the rover and see the condition of the underside of the rover since the landing. And of course, the guys at UnmannedSpaceflight.com have done some superior work putting this together. And so I'm going to share my screen and show you this panorama. So here it is in a wide view. You can see it's made of 1, 2, 3, 4, 5, 6, 7. It's 8 separate pictures that have been merged together. This was a more difficult than usual panorama to build because the camera moved a lot between the shots. So there was a lot of warping and blending necessary to make it work somewhat. But still, what an awesome view this is underneath the rover. Just to give you some sort of wide angle overview, up here are the hazard avoidance cameras. There are 2 pairs. And I think it's this pair that is currently in use. The other pair is wired to the backup computer, so if they ever have to switch to the backup computer system, they'll switch to that pair of HazCams. But hopefully they'll never have to do that. So if we zoom in, you can see some wonderful things in this image, and I'll have to scroll around a little bit. Here's one random little item. You see this little pin sticking out here? That's for static electricity discharge. Mars is so dry and there's all that dust running around. The rover could actually build up quite a static charge. So these little things are called lightning rods. It has 4 of them, and that helps it discharge static. We can go down and look at the beautiful wheels. You can see that they're already coated with very fine dust in some places. Let's see, what are some...
Well, it's important as well. You can see, if you can go back for a second, Emily, you can see the Morse code pattern.
It's actually better. Yeah, it's better on this wheel.
Oh, is it? Okay, yeah.
There we go.
Yeah, so you can see that Morse code pattern, which is cool, but also a way for them to sort of keep track of their distance.
That's right. It's so when they use a technique called visual odometry to measure how far they've been going, the rover knows exactly how many wheel turns it's gone, but if there's any slippage, then the actual distance that it traveled will be different from what its wheel turns tell it. And by counting the distance between the markers made by these sets of holes, they can get a pretty accurate reading on how far they actually went. Let's see if there's a couple of other fun things to point out in here.
And if people don't know, it's Morse code, so it actually writes out NASA JPL in JPL. Morse code. Oh, JPL as it drives along.
Yeah, which is it was supposed to be a hidden way of hiding the name of JPL in the wheels, because originally they actually had JPL machined into these tires. One of the sets of the ridges here was actually spelled out JPL, and NASA nixed that, so they went back and did this instead. Here, this is kind of cute. Up here, you can barely see it, but this is part of the sunshade for the Mardi instrument, the Mars Descent Imager, which is the one that took those amazing pictures on the way down to the landing on the surface of Mars. And I think that's all I have to point out here. Oh, one other little thing that I thought was kind of interesting. You can see that the tracks don't go straight back. They drove to this position and then turned to a direction so that the solar illumination would be good for their arm checkouts. And what I think is cool is that you can see there's a little ridge of dirt piled up by the wheel here as it turned in place in order to straighten the wheel out at the very end of that drive.
So was this to get good shadows and illumination so they could better see the rover, like get it in good light?
That's right. It was to get the arm and the top of the rover in good light. Okay, now,
I had somebody comment actually on like when I reposted that image, and somebody commented and said, this is stupid. Why are they taking pictures of itself? They should be out doing science. But I mean, this is a safety thing, right?
Yeah, actually, that's an extremely good question. Why are they doing all these vanity shots of the rover? And it's for that. It's in order to check out that the condition of the rover is the same as it was when it was in the clean room on Earth, because this is after all one gigantic scientific instrument. And in order to trust your scientific data, you have to have your calibration very careful. You have to know that the machine is performing precisely the same way that it was when it was on Earth, or if it's not, you have to have an accurate measure of how it's performing. Is different now than it was then. So that's what they're going through now, is they're checking out everything, they're making sure everything is operating properly before they try to actually use it for science. And so as cool as these images are, most of them have that kind of functions to check out and make sure that everything's working as they expect.
Yeah, I mean, you can imagine a situation where there's like some kind of rock or piece of dust caught up right outside an instrument that they're about to try and turn in that direction. It might get stuck or jammed into a part of their mechanism. So it's important to get a view like this.
Right. And also, the gravity is different on Mars. So for a lot of these mechanical things, they have to test it under Mars gravity. It should work, but, they got to test it to make sure that it does work.
And it's awesome. So I think it's good.
And it's also awesome.
Yeah.
So I'm going to share now. Here's that self-portrait shot, which is just so cool. And somebody pointed out to me, it's hard to see in this particular version of the image, but if you blow up this part right here, you can actually see down here it's a little orange, up here it's less orange. We're seeing the part of Mars that Curiosity is looking at, but it's upside down because this is a concave mirror inside this instrument. The reason
is it seeing behind itself then?
No, so it's a mirror, so it's seeing in front of it. So actually part of the camera that's taking this photo is also reflected in that mirror.
Right, okay.
So this particular image doesn't look as good as the others because it was taken through the translucent or the transparent dust cover. This is a good example of something that is different than it was when it was in the clean room. When the rover landed, a lot of dust and gravel was kicked up, and a lot of dust settled on the dust cover. So it's a very good thing they had that dust cover on this beautiful camera, because this is what the images would look like if they didn't have that dust cover on. So that's, it's an example of things that they need to check out about why it's quite different on Earth than it was on Mars. Okay, so we're done.
Now, are there any instruments in there? Because it looks like there's a lot of stuff on that.
There is a lot of stuff here. So yeah. I'll point these out. This is CamCam. CamCam is a laser induced breakdown spectrometer. And so most of the CamCam instrument is in here. It has a mirror with a telescope. The mirror is for a telescope. It fires a laser at a target to turn some rock material into plasma, and uses a spectrometer to read the plasma, the spectral lines in the plasma, and that tells you the elemental composition of the stuff that was in the part of the target that they vaporized. But the camera can also be used to take photos without doing the laser part. And so they've been testing that quite a lot. This is another example of something they have to do in this commissioning period. They have to make sure that their pointing is really precise, because that laser spot, you know, it's a very tiny spot. And so they have to point this camera with incredible precision in order to get the sample of the exact spot they wanted to on Mars. And their pointing it's never going to be absolutely perfect when they land. They have to, you know, experiment with the pointing and make some minor changes to the parameters before they get the pointing absolutely perfect.
Right, and you can imagine, I mean, this isn't like a great big high-power laser that's, you know, carving rocks in half. It's creating a tiny little puff of plasma that you need really precise instrumentation to capture it in that instant that it's generated before it, you know, blows away. So
yeah, exactly. So other instruments we have here, these are the two mast cams. This is the wider angle mast cam 34. This is the narrow angle mast cam 100, also known as mast cam left and mast cam right. So those are the beautiful color cameras. They're built by the same company, Malin Space Science Systems, that built Molly and Mardi, and they all have the same detector. So the images from all three of those instruments look rather similar. They have the same kind of color, the same shape, the same qualities, because they're all built with the same components. And so most of the images, the 360 panoramas and all that kind of stuff, is going to come from this camera, the mast cam left, the 34mm one. They'll do high resolution shots with the mast cam 100, which is a 100mm focal length. And finally, you have two pairs of nav cams. So there's a left nav cam and a right nav cam. These are basically identical to the ones that were on Spirit and Opportunity. They're used for taking very wide angle grayscale shots of the surroundings in order to navigate. They're called navigational cameras, and that's what they're for. It takes, I forget the number, I think it's 9 nav cam frames to cover 360 degrees around the rover. And so they spin the head in a circle, taking one image at a time until they have a 360-degree view. One of the things that's a little different from between Curiosity and Spirit and Opportunity is that these cameras are much farther apart on Curiosity than they were on Spirit and Opportunity. On Spirit and Opportunity, they weren't much farther apart than our eyes are. They're actually located in the middle of the mast inside the scientific cameras, and so they have like a human eye separation. These things are separated by 14 centimeters, which is about twice the separation it was on Spirit and Opportunity. So that means the parallax is a lot greater with Curiosity's nav cams than it was with Spirit and Opportunities, and that's taking a lot of getting used to.
But of course the goal here is that you can quickly map out your environment and really get a sense of where all the rocks are from a real three-dimensional view, so that they can plan out their future, you know, the next steps they want to go to.
That's right. It's primarily for drive planning, but it also produces really lovely panoramas. Okay, so here is an example of an image taken with the Mars Hand Lens Imager, fairly close up to its calibration target. You can see all these lines. They're trying to figure out how finely they can focus. I want to focus right here. You can actually see there's some Greek letters written inside the 0 up here. So these are 1 millimeter lines. That's what 1.0 means. And you can say gamma, delta, beta, gamma. I think that's a reference to some fraternity from Caltech or something.
Yeah.
I'm not totally sure.
That's
what people have been speculating on unmanned spaceflight, but I have not actually asked the mission scientists about that one, so I don't know. Here's
now,
another.
was that lines per millimeter? So down at the bottom, you're getting like 5 of those lines in a millimeter?
Yes, that's right.
Yeah, okay.
And down, way down here, it's 10.1 lines per millimeter. So yeah, I think you're right about that. Okay, so here's another part of the calibration target. This is a 1909 penny. Sad story. The mission was supposed to launch in 2009. It was supposed to be a centennial celebration. It turned out to be not quite on the right year, but it's still cool that there's a penny. And just for scale.
Replace the penny?
No, it was bonded. That's what this red stuff is. I thought it was Mars dust, but it's actually this is the adhesive that's bonding it to the calibration target. But they said in the press briefing today that this speck here is a speck of Mars dust, and it's 200 microns across. So that's the kind of things that you can see with this MALI high-resolution imager. It's going to be really great for the geology portion of this mission. Moving right along, this is another MALI picture, and this actually shows one of the instruments on the deck. So this is part of the checkout of their of the science instruments that are inside the rover. This one is ChemIn. It's the chemistry and mineralogy. This one is the X-ray diffraction, X-ray fluorescence instrument. And so this little grating here only permits a certain size of particles to pass through, and that's what they'll the robotic arm will deliver crushed up powdered material into this inlet, and then ChemIn will check it out. And so this is shown with the sample covers opened. I actually have a fun. So this is of a different instrument. This is SAM, Sample Analysis of Mars, and it's just a little animation of Nav Cam images showing the inlet ports opening and closing, which I think is kind of cute. Let's see, what are some other cool images? Oh, this was an interesting image that confused several people when it was first posted on the Raw Images website. I had no idea what it was, but fortunately there's a guy from Mail and Space Science Systems who posts regularly on unmannedspaceflight.com, and he explained to us that this is a depth map. So the MALI camera can take several pictures at different distances from the target to get some parts of it will be in focus and some won't when you're up that close to the target. And this is actually it's basically a digital elevation model of what it was seeing in this ChemIn picture before. So you can see this this part is close to the camera, and this part was far from the camera, and that's what the depth map means, I think. Or maybe I got that reversed. No, I think that should be right. Okay, so fun inlet ports opening and closing. And by the way, the imaging that we're doing here was not just to test out the MALI camera. It was not just to watch and make sure the sample inlets opened and closed. It was also to make sure that the robotic arm was positioning everything in precisely the position that they expected it to be positioned. They were going to what they call teach points for the arm. They start basically every move with the robotic arm by going to one of these teach points first and then deviating from that teach point by a certain amount. And they did all of this arm teaching in Earth gravity, and considering how heavy the arm is and how heavy the turret at the end of the arm is, I think it's like 40 kilograms, they needed to redo all of that teach point checking under Martian gravity to make sure that the arm was where they thought it was going to be when they told it to go to these teach points. Here's some fun animated GIFs of some tests being done on the sample handling mechanisms on the end of the arm. This is the turret at the end of the robotic arm. You can see the drill is over here. This is the alpha particle X-ray spectrometer instrument. And what we're watching move is part of the Chimera sample collection. And Chimera is an acronym, but I forget what it's an acronym for. But you can see a grating that's designed to accept large rock particles. You can see over here there's a funnel, and there's all these different mechanisms that they'll use to portion out and deliver the right amount of the right size particles to the sample instruments. Here's a close-up on that same animation. You can see the little sample cup opening and closing. It's kind of cute. And here we have another portion of the sample capturing mechanism moving. Here's a close-up on that. I don't actually know exactly what this is. I think it's part of the scooping mechanism, but I'm not totally sure. I'm going to have to ask somebody about that. So that's all of my show and tell. There was a press briefing today. They said that everything is going great. They're only about one sol behind perfect, which they said something interesting about that. Apparently back on Sojourner days, they expected to lose 1 in every 3 sols to some kind of problem. Either something wouldn't work on the rover, or they would have made a mistake on Earth, or there would have been some other reason that they lost that sol and had to try to redo the stuff that they had attempted to do on that sol. I know that in the early part of the Mars exploration rover missions, they planned to lose 1 of every 3 sols. But as the mission went on, their average was actually about 1 in 10 sols. So they were doing a lot better on Spirit and Opportunity. On Curiosity, they've gone through 37 sols and have only lost 1. So their record is so far much better, although most of these sequences were pre-canned. So maybe their rate will get a little bit higher as they actually go into the science parts of the mission that are planned each day.
It's kind of surprising. You said 37. We're like a month and a week into this mission. It's flying by so fast.
I know, it's really amazing. Of course, the mission's going to be quite long. It's a Mars year long. That's 687 Earth days. But yeah, we're actually 5% of the way through the primary mission already. It's kind of astonishing how fast time has gone.
So we should queue up ways that people can actually reach us. So if you're watching this on Google Plus, you can just post a comment into the comments below where the video is appearing, and you can do that whether it's on Emily's original post or whether it's on my post or anywhere else it's been shared. It should all come to us. If you're watching this on YouTube, you can post a comment or question there, and we should be able to see it. And then the last thing is, if you're watching this on Twitter, you can just use the hashtag CQX, and we'll be able to spot that as well. And so, you know, as with last time, we'll just take all your questions, and we'll see if we can give Emily some zingers here. So now, did you want some questions? Do you want some questions?
Yeah, I think we're ready for questions. I mean, most of what they've been doing recently has just been trying out our motions and taking these pictures. So there's actually not a lot of news from the mission, you know, because nothing has gone wrong. So there's not a whole lot to discuss about what the experiments that they've been doing recently.
Right, but they also haven't gotten to the point now where they're starting to do the primary mission. They haven't really started to start to examine and climb up the mountain and examine rocks and things. They're in this in-between stage. I know it's like this with a lot of telescope missions, space telescope. You know, the first few weeks they're just testing out every instrument, and often it's really, you know, not great images that are coming back. It's more about testing than it is about delivering really pretty pictures, even doing the science. So a lot of this stuff, although I find this stuff is pretty exciting. I really like to be able to see all of these self-portrait stuff. But you know, let's get to the science. I can see why people are really you know, they're really impatient and want to see that. So, okay, so a question from Richard Saunders, which is, are there any true video cameras on Mars?
Yes, as a matter of fact, all of the mail-in cameras are capable of capturing video at approximately 4 frames a second. It's not quite as fast as an Earth video camera, but then the rover moves extremely slowly, so that's as fast as you really need. They haven't actually done much in the way of video except for what they did with Mardi, and you've seen that. That was pretty astonishing. So I don't know when their plans are to do video. Oh, wait, actually, yes, there is going to be one video. There's one thing that I forgot to show you.
I mean, I'm thinking like dust devils, for example, because there were all those wonderful photographs of dust devils by Spirit and Opportunity, but you could imagine it watching the horizon to see for dust devils actually moving past.
Yeah, dust devils are going to be hard for video because it's impossible to predict when and where they're going to happen. So I'm not sure about dust devils. It would be great if we did catch it. But I can show you something that is going to be caught tonight.
Oh, yeah? Okay.
So let me share the screen again.
Or a dust storm, right?
This is an unimpressive looking image. There is just a dot in the middle of it, but what you're
imagine
actually...
that dot moving in video.
Well,
yeah.
The dot is actually the sun seen through a neutral density solar filter on the Nav Cam. And tonight they are going to be watching a Phobos transit of the sun with video. So that is going to be really cool. The Mars exploration rovers got animations of both Phobos and Deimos transits of the sun. But their frame rate is pretty low. There's several seconds, I think like at least 6 seconds between frames. So at 4 frames a second, this is going to be much more interesting to watch. So I'm really looking forward to that one.
I wonder if that was at all worked into their timing, that they had this planned from... I wonder how often these transits happen.
The transits, there are transit seasons. They have to do with the apparent position of the sun. So I think they happen twice a year, twice a Mars year. And there are lots and lots of transits during that season. So I think there's 3 opportunities over the next month or so to see a Phobos transit.
Right. It's kind of similar how we get lunar eclipses and solar eclipses in rapid succession, because the moon is actually very close to the plane of where the sun is, and so you'll get them, you know, while it's in that place, you'll get them going past each other for a little while, and then the moon moves off of the plane, and then it's nowhere near the sun for a while. So
yeah, on Mars, the geometry is actually a little easier to think about because Phobos and Deimos both orbit precisely in the equatorial plane. So there's fewer different angles all combining to make things happen.
So it's more just about Mars's equatorial tilt, or axial tilt, causing the lineup. So yeah,
and it's also about the latitude of the rover, because apart from orbiting in the equatorial plane, they also orbit incredibly close to the planet compared to Earth's moon. So Phobos is not even visible from some parts of Mars just because it's so close to the equator, so it's so close to the planet.
So a question from Andrew Planet on YouTube. So can you guess or estimate how long the rover will last past its expiry date?
Well, of course, it's impossible to know for sure, but the radioisotope thermoelectric generator, the power source, should provide plenty of power for the rover for 14 years. And so power is not going to be a problem. This rover has a lot more redundant systems than Spirit and Opportunity had. It has two completely redundant and separate brains that are connected to two completely redundant and separate sets of engineering cameras, the Nav Cams and Cams. So if it loses one brain, it's got a backup brain. So I don't know. It's going to be interesting to see what limits the life of this rover. Another thing that this rover has that previous ones didn't is brushless motors, which wear out a lot less quickly than the brushed motors that you have on Spirit and Opportunity. Opportunity is still doing pretty well. It's lost the steering actuator in one wheel, but all 6 of its wheels are still rolling. But that's probably what's going to kill, my prediction of what's going to kill the Opportunity mission. Much like Spirit, it'll finally lose a motor and no longer really be able to drive anywhere. I don't know what's going to kill this one. It'll be interesting to see how long it lasts. It could pull a Voyager. You never know.
Right. Well, the big difference, right, is the power system, because with Spirit and Opportunity, they've got these solar panels, and the big concern when they were originally deployed was that dust was going to collect on the solar panels to the point that the rovers were going to run out of electricity. The big surprise was how these dust devils are coming along and clearing off the solar panels and making it, cleaning it off.
Yeah.
So, but in the case of this, it's actually got this nuclear heat reactor on board.
It's not a reactor.
I know.
It's not a reactor.
Nuclear thermal generator. A nuclear thermal generator. It's got generator, this heat. It's got a big hot thing on board.
It's basically the radioactive source is doing nothing more than being warm.
Yes.
There's no fancy anything really. It's just it's warm and it's a constant source of heat.
If I said radioactive thermal generator, would that make you happy from
yes.
here on out? Okay. So the bomb on board. No. Right. So the radioactive thermal generator on board is completely independent from the outside world. It doesn't matter how much sunlight is falling on the rover. So it's really and it's going to lose its energy in a very predictable rate. As you said, Voyager has been existing on its generator for decades and decades. So as you said, it's probably going to be the motors, it's going to be the wheels, it's going to be that thing's built to last a long, long time.
Yeah, I mean they do have several different communications antennas, so even the failure of the high gain antenna would be a problem, but it wouldn't kill the mission. There's a lot of redundancy built into it, and of course there's a lot of ingenuity at JPL, so if they do run into a serious problem, they will still be able to eke a mission out of whatever they have left.
I think that's a smart way to approach it. I mean, a lot of the missions seem surprisingly short-lived. Some of the missions that have been out there, even Hubble Space Telescope, they only had it set for a few years originally, and then have been servicing it. But I mean, to build in all of this redundancy and all of this just ability for the real long term, I think is really smart, because then it's like bang for the buck. They discover new uses for the rover, for the observatories, for the telescopes once they've been using them, and they keep getting tons and tons of science out of them. So to really build them to last, I think that's the key. Let's take another question. And thanks to, or welcome to, all of the German viewers who are now able to watch us live. I know that for a long time there, anyone in Germany wasn't able to watch a live video on YouTube.
Huh.
Yeah, it was I don't know, the German government wouldn't let them watch it because of some copyright issue or
weird
transmitter license. I don't know what it was. But anyway, that's all been worked out. So this is a great question. This is from Adam Waller. Is it possible for MSL to take pictures at night? And if so, why haven't we seen any? And I'd like to sort of take that even further, which is, is it equipped? Is there some extra science that you might be able to do at night, taking pictures of the landscape?
Well, both Spirit and Opportunity have taken nighttime photography, astronomical photography.
Yeah.
I'm not sure that there is much of scientific value there. I think it's mostly done because they had extra power and it was cool. For Spirit in particular, when Spirit peaked to the top of Husband Hill, had such a good power condition that they were actually running warm. They needed to use instruments at night in order to get rid of some of the power that they had. So they did these astronomical observations. It was really fun. But I'm not actually sure if there's any real unique science that you can get out of that. I will have to ask somebody the answer to that question.
I mean, I'm just thinking anything like ultraviolet, or, you know, if there's some kind of reflected light that you might get from, you know, I mean, I know in this case the moons aren't bright enough to really cast shadows and give it any function, or infrared, if you could spot at night any kind of infrared sources, maybe some kind of I don't know, thermal, something coming out of the ground, you know, like a geothermal source or something.
The
Bacteria,
activities,
colonies.
yeah. Well, although the cameras do have the ability to image in the infrared, it's the near infrared. There's nothing thermally radiating at the wavelengths that would produce thermal radiation at those wavelengths. I know that they will be, or at least I hope that they will be taking a sunset video at some time. That's going to be really special.
Yeah, and there's definitely going to be some astronomical, I mean, you know, getting the shot of home, getting that view of Earth in the sky is always a crowd pleaser, so I'm sure they'll do that at some point.
They won't do it soon, because they have to focus on the first commissioning the spacecraft, and second getting their prime science mission done. I did want to mention, there is one other activity that they do at night. A lot of the laboratory instruments and the contact science instruments, they like to run at night. So APXS, for instance, gets much better signal. Both X-ray instruments get much better data when they're operating at night. So APXS would operate overnight, and the ChemIn XRD, XRF instrument will also be doing most of its analyses at night. They're also, especially the ChemIn and SAM, are power-intense instruments, and so really the rover can't be doing anything else while it's running one or the other of those.
Okay, now we got a million questions, so we'll go through them. Okay, so so this is a question from Peter Trussell. Does the rover operate through all the seasons, and will shutting it off and on shorten the life of a rover? So
yeah, so this rover will, like its predecessors, be able to operate in all seasons. Now, you think that because it has an RTG, it won't be so it won't be so dependent on the sun as Spirit and Opportunity were, because they were solar powered. They often had to park during the winter in order to tilt their solar panels toward the sun,
and not die.
And not die, yeah, exactly. So Curiosity is not going to have to do that, but it still has much higher power demands during the winter than it does during the summer, because a great deal of its power goes just to warming up the motors, or warming up, like the camera instruments have to be warmed up before they can be used, which is, by the way, one of the reasons why almost all of the images that you've seen so far have been taken after local noon. Most of them come from the afternoon, especially the color ones.
So it's spending that initial time just recovering from a cold night?
Yes, exactly.
Right.
Because the temperature drops by 80 degrees Celsius overnight, and so it's quite chilly. Things do get very cold, and they have to warm up. So during the winter, it's much worse, the cold conditions, and so their activities will still be limited during the winter. They won't be able to drive as far. They won't be able to image on as many days, or use as many science instruments on the same day as they can during the summer. We're headed into the summer right now, though, so things are looking. Oh, wait a minute. Are we heading into the summer? Now I've lost track. Yes, we're heading into the summer, so it'll be good for power for a while.
Yeah, I'm trying to think. That's what they would normally want, is it to be?
Well, it's what they would.
Summer, but it's all about
what they would want. But it's all about where they picked the landing site, right? Because if they picked a Northern Hemisphere landing site, then they'd have wound up being in the opposite season.
So, okay. So this is a question. Comes from Jove Landsman. What would be the apparent size of Phobos in reference to the Sun during a transit? So how big is Phobos compared to the Sun from the ground?
I'm looking for a visual aid. Actually, this one is not bad. So this is the little disc that covers the little port that puts your cables down in your computer. And so this, the gap in this disc, it's a bit larger. I say it's maybe not quite twice as big as Phobos will be. It's not much smaller than that. This is not a bad reference. So Phobos will be a dot crossing the disk. It's a transit, not an eclipse. Deimos is much smaller than that. Deimos is a dot. It'll be visible in the images, but it's a pretty small dot, because Deimos is a smaller moon, and it's also much farther from the surface.
Okay. So this is Trevorsaur Videos asks, how far in kilometers roughly is the rover expected to travel in its mission?
You know, that's a question that I've often asked the mission managers. You know, the Spirit and Opportunity had very explicit goals for how long they were supposed to drive. Mission success was defined at 300 meters. The rovers were designed to a target of 1 kilometer. Of course, now Opportunity's gone 35 kilometers. For Curiosity, they actually do not have a set distance goal for the rover. All of their goals are science goals. So the rover could go 10 kilometers in its primary mission, but if the science is compelling enough, they're not going to force themselves to drive farther just in order to hit that odometer mark. I forget the precise distance to the mountain. I think it's a couple of kilometers. So they'll definitely drive that distance, and then they're going to be tootling around the bottom of the mountain and probably not covering a huge amount of distance between science sites, because I think the stuff looks really compelling, even right at the base of the mountain. It's going to be pretty exciting.
Okay, so this question comes from Russell Bateman. With dust being a problem on Mars, what systems does Curiosity have to remove the dust or keep it off? Is it going to rely on dust devil buddies too?
Well, of course, the only systems that really care all that much about dust are solar panels, and Curiosity doesn't have those. The one interesting complication that the unexpected amount of dust that was thrown up during the landing has caused is that the rover has these calibration targets. They're, you know, patches of white and black and colors that the cameras and stuff are used to point at to make sure that they're to sort of color balance them. And all of those calibration targets are covered with dust now, more than they expected. So for instance, the Molly calibration target, which I showed you earlier, the white and black panels on it are actually probably kind of useless for white balancing right now because they're covered with dust. Fortunately, the rover is painted white, and there are much less dust-covered surfaces that Molly can image and get a better white balance that way. But there's really nothing else that I know of that will be badly impacted by dust, except for eventually you'll get the problem that Opportunity has, which happened during a major dust storm where its camera optics got covered by dust, and so the images are of much lower quality than they used to be because it's shooting through all this dust. Eventually that's going to happen to the mass cams and the nav cams, and it's kind of unavoidable. And they can still work around it. Now, Molly has a dust cover, so that one should remain dust-free throughout the mission, unless, of course, they have a problem with the mechanism that drives the dust cover.
This question comes from Riding with Robots, which is I'm assuming that's the name of the blog, which is a great blog, and you should totally check it out. So what's left to characterize the rover at this point? Are there any tests that still need to be done?
So they're basically done with the arm commissioning and the commissioning of what they call the contact science instruments. So these are the instruments that you can use on the robotic arm, you put it up against a rock and you get science that way. That's APXS and Molly. There's one more test they have to do to finish that part of commissioning, and they talked about it at the press briefing today. There's something called organic free blank material that they will drill into and use as a calibration for the belly instruments, the SAM and ChemIn. And they're doing what's called a preload test, where they put the arm up against it so that its contacts are touching it, and they load it with a certain amount of force, which is what they're going to have to do with that arm before they can drill into anything. And then they're going to leave it there, loaded in that way, overnight to see how the changes in temperature affect the force with which the arm is pressing against the rover. That extreme change, most of the rover is built out of aluminum. And it's kind of hard to believe, but the aluminum actually shrinks. When you consider how big the rover is, the rover actually shrinks and enlarges by a couple of millimeters over the course of the Martian day with that change in temperature. And so you can imagine that might affect the amount of force that they have loading the arm onto a target. So it's very important for them to check this out. So that's the last thing they have to check tonight. Then they will drive, is what they said in today's press briefing, until hopefully they find a good rock to do their first drilling test on. Now, a good rock will be one that is big, relatively flat. It'll be better if the surface is is very flat rather than at an angle, because they do have to load that arm, press down against the surface. And so if it's at an angle, you can imagine it just shoving the rock instead of loading against the surface. So if they see what basically looks like a paving stone is what they're going to want to find in order to do their first drill. And that won't be picked for science reasons, it'll just be picked for engineering reasons. Although, any rock on Mars is going to be interesting to check out. So that's what they'll do. That's the last thing that they have to do, is to do their drilling and the first delivery of material into the SAM and ChemIn instruments. That testing I'm actually somewhat apprehensive about, because I remember the Phoenix mission, which also had to drill, take samples, and deliver it to instruments. And that mission had an absolutely terrible time getting material into its instruments. Now, Phoenix had a bad time because of some machining problems, actually, with the instrument it was trying to get things into. But basically everything on the sampling part of that mission was harder than people had hoped. And so I suspect that they're going to run into problems that they weren't able to predict, and that they'll be able to solve them, but that it might delay us while they try to figure out how to get these samples inside these instruments.
Another question here. This comes from Richard Frederick, which is, how often will they decide where Curiosity is going to be doing its science stops? Have they got a grand tour all figured out? Or are they going to be choosing their locations as they go along and find interesting things?
Well, it's a little of both. So Curiosity has an advantage that Spirit and Opportunity did not have when they landed. Curiosity has the mapping power of Mars Reconnaissance Orbiter's high-rise camera to give it reconnaissance maps. So they have actually mapped out in extremely great detail in 3D all of the different kinds of rock that they can see from orbit, and they have several traverses outlined as being possibilities for the rover. So the kind of general roadmap, or at least a few general possibilities of routes, are definitely mapped out. However, the reason that you send something to the surface is because you see things when you're on the surface that you can't see from orbit. And so undoubtedly they will be seeing things that they didn't notice in high-res images, and they will go to check those things out because of what they saw on the surface. Curiosity's mission is going to be a punctuated one, where there will probably be a long drive followed by several weeks spent at a site doing these kinds of careful sample acquisitions. So it'll be a sort of site drive, which is kind of what the other rovers were doing, but even more so.
But you could see a situation, especially with this reconnaissance mapping, where they might analyze a certain kind of material with a certain chemical composition, uncover something really interesting, and then go, can we find any more patches like this that we're going to want to go and check out? And then they're going to find a bunch, and then they're going to route the rover towards those things. That definitely wouldn't be out of the question.
Yeah, absolutely. Although the direction that the rover is eventually going to be headed is up into this mountain, and so there aren't actually that many paths into the mountain that the rover is capable of traversing. Just like any other mountain climbing, you can't just draw a line and go straight up unless you're an idiot. You look at your topographic map, you figure out the easiest way to get up through the pass, and that's what they have to do with this rover as well. So they'll probably settle on one particular trail up into the mountain, but then they'll be diverting to the side in different places to go check out different targets as they find interesting things.
So this comes from Robert Scott Herrick. Are there any plans to use the Sky Crane on future missions?
That's a good question.
Yeah.
I do not know of any plans to use it on any future missions. It seems a shame because it's so cool how it works so well. But no, currently I do not know of any future plans to use it.
How well do you think it would scale up? I mean, this is something that we actually covered in Universe Today a couple of years back. That the problem with Mars is that it's got an atmosphere that's too thick, so you can't, but it's also too thin, and so it's not this happy medium. Like on Earth, the atmosphere is nice and thick, and so you can actually air brake into the atmosphere, and then you can use parachutes and land very gently. But on Mars, it's still enough atmosphere to kind of burn you up, but not enough to let you use a parachute to land. And so you've got this, and if you're looking at like really big cargoes, like spaceships filled with humans, and landing that, it's a very dangerous process to do it, and there's no, can't use an airbag, they get all squished. So the Sky Crane sounds like a really smart way to do it. I wonder, if that's something that they'll consider for future missions. But I guess in this case, really, it's about coming up with something that prevents the dust from collecting back up into the rover.
Well, they'll probably just shield things a little bit better in the future. They could have added covers to those things. They just didn't predict this particular problem. But as far as the sky crane scalability is concerned, I'm not an engineer, so I don't really know. It doesn't seem like it would be a terrible difficulty to scale it up a certain amount. Actually, a bigger problem, I think, is the heat shield, because that was one of the sources of a cost overrun on this mission, was the fact that as they modeled what it was going to do as it entered the atmosphere, as the weight of the rover got larger, they discovered that the material that they had planned to use for their heat shield would not be able to survive the temperatures that it reached. So they actually had to switch to, I think it's the shuttle tile material for their entry, because it was a hotter entry than anyone into Mars in the past.
Oh, when did you want to go till?
Emily? Oh, I do have to leave sharp at 5 today.
Okay, so we'll cut it off at 5. I will try to manage the time then.
Thanks.
So this is a question I'm not really sure the answer here, and I'm not sure exactly what they're getting at. So Rarian Rakistra asks, does the rover use standard IEEE data transfer protocols or NASA specific ones?
I honestly don't know what format the data is in as it's transmitted to Earth. I pretty much only work with data after it's come through the Deep Space Network, been transmitted to JPL, and decoded into what's called the PDS format, the Planetary Data System format. They have their own data format. There's various software out there that can turn it into data of the types that you're more familiar with, like ping or TIFF or whatever. But I don't know really very much about how it gets transmitted from Mars to Earth.
Yeah. Because, I guess the question is, could anybody with a large enough dish be able to tap into that signal? I don't think it's encrypted in any way, is it?
No, I don't believe it's encrypted. You do have to know how to decode it.
Yeah. And you need to have a dish like the size of either the Deep Space Network. These are all huge dishes around the world to capture this faint signal from Mars. And
remember that most of the data that comes from Mars doesn't come directly from the rover. It comes through one of the orbiters, Mars Odyssey or Mars Reconnaissance Orbiter. There are amateur radio astronomers who have reasonably big dishes, and they've detected the signal even from Voyager, but they're detecting only carrier. They're not getting data from Voyager. From missions that are much closer to Earth, though, they can definitely decode the signal. I don't know what they can do with that, though. I don't know enough about the field.
Yeah. Where was one here? Okay, so Guido Bibra asks, so we heard about one of the wind sensors being damaged on the landing. Any update on where that's at?
No, there was an interesting question asked at the previous press briefing. Somebody said, can they use the MOLLE camera to check out what happened to that instrument? And the answer is maybe. But it's not easy, because that particular temperature sensor is on a boom that sticks out from the neck in precisely the opposite direction from where the robotic arm is mounted. So it's a really awkward angle. They have to kind of get the arm out like this, and they can only get within about half a meter of the damaged boom. So it's not clear how much useful information they could get from that. So what the mission manager said is that there are not currently any plans to do that imaging, because it probably wouldn't really help them very much. But it sounded like it was something that he might be willing to do at some point in the future after they've settled down on the mission after a while.
So this question comes from Josh Andrews. How far up could Curiosity get? Will we ever see a Mars landscape outside of Gale Crater?
That is a good question. So in order to
see,
see
that central peak is higher than the crater rim. So if it gets a little ways up the mountain, will it be able to actually see out onto the landscape, I wonder?
I think you would have to be seeing through a part of the rim that was very low, through a notch in the rim, because the Curiosity is probably not going to peak this mountain. And actually, it's not going to go particularly high up, at least on its first climb, because all of the layered rocks are in the base. And then you get right above the interesting layered rocks, you get to something, the difference in its appearance is quite striking, even on the images that you get back from Mastcam right now. It erodes into these very sharp features. It looks like a wind-deposited volcanic ashfall unit. They call it the Yardang forming unit because it makes these funky shapes that are called Yardangs. You can look it up, Yardang. And
what's a yardang? Sorry.
a Yardang is a
Aren't
wind.
those like they look like they're in this, like you see them in sand, right?
Yeah, they're wind eroded topographic features. They look kind of like teardrops or
Yeah,
spear
right.
points.
Yeah.
There's a place in I think Mongolia that has some really impressive ones that look a lot like the ones that you see on Mars, actually.
And I remember there was a story we worked on about 4 or 5 months ago where someone had some pictures of some yardangs on Mars, and they were discussing some of the interesting, because the atmosphere is very different on Mars, you'd have a different kind of shape. But these are actually like carved into like sandstone rock,
Yeah.
right?
Yeah, and so these two are carved into some kind of rock. It's not clear what kind of rock it is, but it's almost certainly not the kind of rock that Curiosity was sent to look at. So what they are planning to do, at least the current basic plan, is to go up this valley and get as far as the contact between the layered rocks and the Yardang forming unit, which is a geologic unconformity. It's a place where there's some kind of gap in the geologic record. And they want to investigate the nature of that unconformity. What happened on Mars that changed the environment from one that formed these layers to one that wasn't forming those layers or was even eroding those layers. And so they'll go as far as the contact, but they do not expect to climb up farther. They'll probably come back down the mountain and go up another place.
Okay, so one question then, this one comes from Ulysses Adkins, which is about how bright is the sun on Mars compared to Earth?
I should have that number off the top of my head. I don't. Obviously, Mars is farther from the sun than Earth is. It's about 1.5 times, and it's the inverse square, so you're talking about three times weaker. Is that right?
Inverse square law, inverse cube law, I think.
So
Yeah.
anyway, so obviously the sun is weaker. However, you have much less atmosphere. There's much less scattering. So the sun itself is actually very bright because its light is less scattered. So it'd still be very hard to look at the sun. I don't know what the difference in exposure settings is for these cameras. The cameras obviously have different kinds of. Actually, no, it's an off-the-shelf detector. So it's the same kind of detector you use in. It's a Kodak detector. So you could compare. I don't know how the exposure times differ between Mars and Earth, but I get a question a lot, which is, those pictures on Mars look bright, but isn't it darker there because they're farther from the sun? And the answer is, with cameras, you always adjust the exposure to have as many photons as you need to make a good-looking picture. So it's all about exposure settings.
Right. So if a person was running across the landscape, they might look a little blurry compared to if them running across the landscape here on Earth because you're setting a longer exposure. But really, it's not going to make that much of a difference.
And you really notice it in pictures from Voyager taken at Uranus and Neptune, because they had to take incredibly long exposures in order to see anything on the moons at that distance from the sun. And
with the spacecraft moving very quickly and
yes.
causing some problems to the image. Okay, great. So got time for just a couple more questions. So if anybody's got any other questions, please let us know. Okay, so this question comes from Bug999. I've seen some news stories saying that MSL won't be able to do some of experiments if it finds evidence of current water at its location. Is that true?
That's a funny one because it's actually not a new story. Space.com was reporting this in November. I haven't looked into the story in any detail beyond what I've read on Space.com, but what I read in that article was that the mission didn't quite follow a protocol they were supposed to follow, and that is a problem. The mission should be following its protocols, but there really isn't any danger. They're at an equatorial location. The possibility they really can't encounter ice or liquid water at this location because it's so warm that it would vaporize instantly at Martian atmospheric pressure. You would have to dig in order to get to water, and they're really not going to be digging. So they have a drill, but the drill only is going to go a few millimeters into any particular rock. So it's really not a problem for this mission, and that's what the JPL people were saying. They're like, "Oops, we should have followed that protocol." But the reason that we didn't is because it wasn't a serious concern. Now Curiosity did not have to follow the most stringent planetary protection guidelines. Phoenix did. So Phoenix was a spacecraft that was explicitly sent to Mars to touch water. And so its robotic arm was sterilized and sealed in what they called a biobarrier before they launched it. And one of the first things that they did, and the scariest moment for their mission, was deploying the biobarrier. Because if that thing didn't come off, then they wouldn't get to use the arm, and that would be no mission for them. So for a spacecraft that is intended to find water, they definitely have to take those kind of precautions, but it's really not a problem for Curiosity. It's just too warm at their landing site.
One last question. Oh, well, right. I was going to say though that you know, if something really amazing happens, then they could very well get caught up in any one location. As you said, liquid water might be a problem, but if they might find something else that's on the mission that they've been looking for, you could imagine them sticking around one location and studying it for a long, long time. If there's a lot of places to sample and a lot of things to look at, you know, or like a field of dinosaur bones, for example, would keep them.
That would certainly keep them occupied for a while.
Keep them occupied for a while, right? So, good. Okay. Well, I think that's all of the questions. So this is a question I don't know about this one. So this comes from Andrew Planet. I guess we'll take this as the last one. So tell me if you know if NASA has plans to, I think he's saying seed. Yeah, seed the polar caps with photosynthetic bacteria. Have you heard the?
I can affirm, even without having talked to anyone at NASA, that NASA does not have plans to do that.
I figured as much. Yeah, I just needed to be sure, though. So, yeah. Yeah, they won't be seeding Mars with life yet.
So I might as well finish with what I'm looking forward to on the mission for the next couple of days or next several weeks. So the rover's going to be driving a little bit before it stops again to do this first sampling. They're heading toward a location that they have named Glen Elg. And Glen Elg is a really good example of something that they picked out as being interesting in the orbital data. It's not a spot that they can actually see from the rover at this point, but it's a place where if you look at the Mars Reconnaissance Orbiter picture, you see that there are 3 different kinds of materials on the surface that are all meeting at the same location. So if they drive there, they're going to be able to get off of the material that they landed on and see 2 different kinds of materials and test all those and understand what's different about them that makes them look different from orbit, which is a great thing to do with a spacecraft, because if you can do that at one location, you can generalize those results to other places that look like those 3 different kinds of rocks from orbit. So that's going to be interesting. While they're doing that, I have to say that the thing that I am most looking forward to over the next couple of weeks is as they drive, they're driving kind of parallel, tangent to the mountain. And so they're going to get eventually some really good parallax on the mountain. And so we're going to get some beautiful, once we get a really good panorama, we've already had one panorama from the landing site. When we get a second one, we're going to get great color 3D on the mountain. And that's the thing that I'm most looking forward to in the next couple of weeks.
Have you got your 3D glasses ready? Perfect.
I'm all set.
Those are really nice. Those are really fancy ones. Where'd you get those from?
People ask me, where do I get 3D glasses? I say, Amazon.com, where you can get lots of other great products. They're really cheap, actually.
Yeah, I'll get some on eBay, maybe. Okay, well, one last thing. This is a comment from Michael Bramble. Emily, thanks for all the planetary science communications and updates you do through this and other mediums. It's greatly appreciated and enjoyed. And I think I can. I think I speak for everyone who's watching that is amazing to be able to talk to you and hear you kind of explain what's going on. We're going to be coming off hiatus. We're going to be starting that tomorrow. So that's on Thursday, 10 a.m. Pacific, 1 Eastern, 6 in London. And then we're going to be doing our virtual star party on Sunday night, where we're going to be hooking up a bunch of telescopes to see a live view of the night sky, and you can see that in a hangout. Last week we had Uranus and Neptune for the first time, so that was really amazing.
All right, well, thank you everyone for staying, for tuning in to this broadcast. And again, I'm Emily Lakdawalla for the Planetary Society. I blog every day at planetary.org. So come check us out. Come check out all the pretty pictures that I post from not just Curiosity, but all of the other missions that are active right now. There's like 20 active spacecraft in the solar system. So do come check us out, support us, donate, or join the Planetary Society. We are a nonprofit membership organization that depends on member dues and donations for all of our activities. So help us out.